Right. So today's lab is on sequential data. So today's lab is going to be on something called sequential data and RNNs. So far, what we've been learning as part of our course and as part of the labs has been about neural networks, standard neural networks, and convolutional neural networks. After that, we looked at some computer vision problems and just how to generally deal with certain problems that take place that arise with using PyTorch, right? We looked at the data loader and how to use it appropriately. We looked at a little bit of data augmentation, how to do what to do when your data set is a little smaller. Today we'll be looking at something which is significantly different from all of that, but still inspired and based on the standard concept of a neural network. So a recurrent neural network is essentially something which remembers its past data, right? Because if you think about it, the neural networks we've had previously, so I'll just write down here, neural networks previously did not have any concept of previous input or memory. Here we want to change that slash outputs and memory. Here we want to sort of remember what the previous input was because our next input is dependent on the previous input. So think of like a financial think of time series, right? When you're looking at the price changes of a stock, at every let's say at every second you get to know the new price of the stock, right? So for you it's a time series where the previous input will almost certainly affect the next input, right? And this is important because without knowing the previous input, there's no way for you to predict the next input or the next output. So your model can't work. So if you use a standard neural network, it will only use all of them equally without like assigning any weightage to how old that certain data point was. So let's say one data point is 20 days old or 10 minutes old, right? That's going to have a lower weightage than the data point that took place just now, at least for a very basic simple understanding, right? So that's essentially why recurrent neural networks were introduced. So I will just show you an image so that you have an idea of what we're sort of looking at. Can you see my screen? So essentially what's happening here is that let's say this is your neural network block, right? And this is your input and this is your output. So what this arrow represents is sort of what's taking place here, right? So for every input, let's say I have an input at t-1 that goes into my neural block and I get an output. And I get another passing through input to my next block from here, right? This has to go in here. And there are mathematical ways to define what V is here. We will discuss those later. And this will impact the next output that you have. So the next output will be a combination of U and V. Does that make sense? No question, so I'm going to assume that does. So what we'll be doing here, I'm sure everyone's familiar with ChatGPT and that it's a generative AI model, right? We'll be building a very, very rudimentary generative model for text today. So rudimentary, in fact, that we're probably going to use like 3 sentences and try to see how it predicts that. So we'll do, hey, how are you? Roughly the same length. I am fine. And we'll do, have a nice day. And the problem statement, essentially what we'll be going for here is that every time I input a letter H, it should automatically be able to predict either how you or otherwise. That's sort of what the problem statement model is. Additionally, let's say I want to input full word. Let's say I write good and I want the model to autocomplete space I find for me. Then it should be able to do that. So this is essentially what we're training for, or what our end problem statement is. So obviously we can't do that arbitrarily, so we'll have to assign like numbers to these characters in our data, right? So we'll make a set for them. And text. And chars also. Right. So you can see that here we've got, actually I'll just make this all lowercase so that it's easier. Otherwise, since we haven't like explicitly specified how we're going to deal with capital and small letters, so we sort of need to look at, so we'll be looking at small letters only because we haven't sort of shown it what to do now. So we'll now create an integer map, and I'll explain why we're doing this in a second. So the reason why we're doing this and why we're assigning numbers to these maps, to these characters, is because computers need to understand some sort of numerical data, right? And you can't really get by with leaving them as characters and hoping they'll be understandable. Now while I've created an integer to character map, I also need to create a character to integer map. Why? So that while decoding it, so that when the uh, model receives an input, it makes sense to it. So I'll just reverse the thing, right? So I'll write char map. Um, int map dot items. And as you can see now, this has just been reversed. So the number of unique characters we have here. Should be 17. It is 17. And now we need to check something which I will again explain in a moment. So what is the maximum length of the characters in the text? There is no such function called max length. So the maximum length of the sentences that we have is 15. Now, why is this important, right? Because what our model is essentially going to be doing, it's going to be taking in, let's say, 3 letters of input, and it's going to be outputting the full sentence. Now, it can't output variable lengths of sentences because our model can't account for that yet. As you know, higher level models and higher level NLP models can output varying levels of what do you call it? Text. That is because they function differently to standard RNNs. Here, since we're building a very basic RNN, it can only output a fixed length. So if you think about it one way, an RNN is essentially something that takes in a variable input or an input lesser than the size of the maximum output and outputs a fixed like length in terms of whatever it's trying to output there. Now, if you remember back to what we were doing with, no, not here. If you remember back to what we were doing with regards to CNNs, right? We used to create batches, and all batches had to be of the same size, right? Otherwise, it didn't make sense. So if you remember, we used to have arrays of let's say 1,000 by 28 by 28, where 28 by 28 is the 2D representation and 1000 are the number of images which create the 3D vector, right? So all batches had to be of the same shape, essentially. And for our, as you can see, the maximum length here is 15. But just a second. I think we'll pad it to 17. Right, but the number of unique characters we have are 17, which means there are 17 possible outcomes that can take place. So we really need to create, we sort of need to pad this to a certain output, right? Now, what do we really need to pad this to? So we need to pad this to 15. Now, if you look at, now let's just look at the entire length, right? Let's look at length of text 0. That is 15. Now text 1, I believe, is smaller. It's 14. So this is not a fixed output with regards to our RNN, which means it's not of the same shape as the rest of the members, not exactly of the batch, but they're not. It's not the same as the output we want to assign to it, because we can pad a smaller number up, we can't pad a higher number down, right? Again, like downsampling is easier, is harder than upsampling. If you also remember padding for CNNs, when we were putting them into when we wanted to keep the size same because we wanted to apply a similar convolutional block, we used to pad it with zeros so that we can maintain the same size. Here we're essentially doing the same thing except for padding with spaces. Padding with spaces to maintain size. So for max length. So now if I print out text, there is going to be a space appended here because now this is going to be of length 17. All right. So now we sort of have to define an input sequence and an output sequence for our model, right? Why are we sort of doing this? Because we need to give it some sort of training set and some sort of output, right? What is it supposed to predict? So we'll create an input sequence. An output sequence, target sequence. And okay, nice. Autocorrect, autofill. Anyway, so what's essentially happening? Stop. What's essentially happening here is that we'll take the. I hope you can see this. Just a second. Right. So this is taking it from the start to the end -1. So -1 is the second last character because Python allows you to wrap around. And here we're sort of skipping the first character and taking in the rest of it. And you can see that the last character has been removed. So pretty straightforward. And I'll also show the target sequence. Which is the first character removed. All right. So this is mostly what our dataset looks like right now, right? Now what you sort of need to think about is that if you remember earlier, we had discussed that it can't accept characters. It needs to accept some sort of numerical value. And we had created a map here, right, from characters to numbers. Now we need to create that, we need to sort of do that map again, right? For our model, for our input sequence and our target sequence. So we will do that, which is pretty straightforward. And similarly for output sequence. So now you can see that your input sequence and your target sequence will look like this. Just a word of caution, in case you're replicating this side by side right now, you might notice that these values don't exactly correspond with what you're doing. The reason for that is when you create it using a dictionary or a set, it's sort of randomized. It doesn't assign a priority to certain things. So let's say I've done 0, like 0 corresponds to G for me here, like it might correspond to R for you. It's randomized. So this is not going to affect our final output because it doesn't really make a difference. But just in case you're like following along, or in case you will be doing this later, I'll just add in a note that usage of set applies. Usage of a dictionary will allot these numbers to characters randomly. Therefore, these exact arrays, exact lists for input and output sequences may not match. Now this is in because I forgot to do text, and this should be okay. Right. Now, if you go back to loss functions, right, sort of think about how loss functions really work. The most basic loss function and the one we've studied so far has been like Euclidean distance, right? You find the distance between two vectors, and that is sort of how far away they are, and therefore that's the loss, because it's not where it's supposed to be according to the ground truth in the data set. So when we look at loss, it's supposed to be, it's for right now, it's generally the distance between two vectors. And you can think of this in multiple ways, right? Let's say I have a single output, which is the probability of yes or no, right? So it's greater than 0.5 is yes, less than 0.5 is no. And let's say it's supposed to be 1, but I get 0.6. So it's 0.4 away from what it was supposed to be. So you use your mean standard error or mean average error or mean absolute error based on what your model type is like. For us, we've pretty much been using MSE for a while now. The distance between two vectors. And right, that's about it. Now, when you look at numbers themselves, right? Let's say I put in H, and the outcome is, hey, how are you? Right? But instead of like predicting, so when I put H, the what it predicts instead is, hey, like let's say Jao are you, whatever, any random character, it doesn't matter. Right? Now the problem here is that the error between, let's say, J and H is now going is it might just be significantly higher than what is the error between W and, let's say, P. It's the ground truth between W and P, which means the H and J like misstep is going to be significantly higher. The error considered for J and H is going to be significantly higher than the error for P and W, because right now we're looking at these sort of values, right? Let's say 5 and 2. So let's say I assign I'll write whatever. Let's say W is 1 and P is 2, while H is like 3 and is on time disconnected. Never mind. While H is 3 and J is like 10. Now, what ended up happening here, right, is that the error for H and J is going to be so massive that your gradients will sort of that after gradient descent, it's sort of going to learn only to not predict J and H. So this is going to be a very strong gradient as compared to this, which is going to be a weaker gradient, which is not something we want, because they're both errors for us, right? And they're both equally errors for us. It doesn't matter to us whether W is replaced with a P or H is replaced with a J, at least for now. For certain problem statements, you might have um, different situations where you might need to look at certain errors being more than others for certain character values or certain word values. We haven't looked at word embeddings today. We might look at that next class. But for us specifically right now, these need to be the same error. So how do we really bring that in, right? So the process is now what we're going to be doing here is called one-hot encoding. Uh, for those of you who have done digital design, I'm sure you will remember what one-hot encoding is. You sort of vectorize a character into another character, into a vector space where each character is is like orthogonal to the other. I hope orthogonality is still 90 degrees. I don't remember. Yeah. So the point is that you need to have orthogonal vectors for each of your characters, so that when you do calculate error, the error is going to be exactly the same, which is like 1, right? And that's sort of what we want, so that at least for missteps like these, for the example I've shown here, the error remains exactly the same. So how are we going to one-hot encode this, right? I don't think I've imported anything yet. Imported numpy as np port torch. So now we'll just add one-hot encoding function. It's going to accept the sequence, number of unique characters, um, sequence length, and batch size. I'll explain why we're doing all of this in a minute. So features. How do I make this go? Just a second. Just refresh this. Never mind, it's gone. Right, now we'll do this for each sentence for I in range. That size. And for you in range sequence. Okay. Oh, F. This should okay. That should work. So this is not pretty straightforward code to understand. What we've done is we've taken a full zero vector and we've put one every time. Like we've put one um, for every vector. So I'll put in a set of features and you'll see what I mean, right? So I'll do input sec one hot and cold and p input sec. Characters. And open this 15. Hard values for now. Change this later. And that size. Probably and that size is not fixed. And sequence length. That's minus one. Just a second. I don't see what the problem is. For access 2 with size 16. Yeah, terrible debugging practices. Should not have been 40. Should have been 16, I think. It was 14. Okay, so we'll come back to this later in a bit. There is also a one-hot encoding function you can use. I don't seem to see what the error is immediately. But, right, so we'll first make the model, then we'll see what is wrong there. So, same practices we've followed before. Um, PyTorch code is nearly exactly the same always when it comes to model making. So PyTorch gives you the option to sort of create an RNN without really caring about what's happening inside it. For the API call. So the RNN API makes it very, very easy for you to actually implement a recurrent network in literally a few minutes. Like if you can pre-process your input data, model building is incredibly easy. Um, is sort of annoying sometimes because it's not as easy as it looks. It turns out to be a pretty complicated um, what do you call it? A pretty complicated piece of work otherwise, but never mind. So ideally we would have implemented this from scratch, but it's actually pretty difficult, like to the point where it would take a long time to do it from scratch. But I would recommend if you're interested, you can actually go through the original paper on recurrent networks and implement the paper from scratch. Since you'll be using PyTorch, it's not a from scratch purely because you are using a library. You aren't just doing it with like Python and NumPy, which is what a true from scratch would have been. But here, essentially, we've done exactly the same thing we've been doing for the past three labs. Mm, Runtime is if it's not cheeky, then you will have a problem. Yeah, we can do this. Yeah, not to complete was code here. So the reason we're sort of having to do this is because why is this invalid syntax? Okay, again, we'll worry about that later. Right, so again, standard practice, take a model, size, number of unique characters, output size, number of unique characters. We'll keep the hidden dimension to be 12. Play around with this later. And the model is pretty small.
The NN dot linear function has a wrong input. Yeah.
All right. Thank you. All right. Yeah. We'll run it for 100 epochs, I think. I will overfit it. See what happens. Keep it large. So we'll use cross entropy loss. Okay, I like how this does it for you. But yeah, it is sort of a classification problem if you think of it. So all cross in all classification problems use cross entropy loss, so we'll use that. And right, now I have to go back and fix some consequence. What is the issue here? Just print it all out. See what. This is a 14, number of unique characters is 17, and sequence length is 15. Okay. Um, your sequence is our input length. So that is 3 cross 14. We're running it 15 times. So this is the problem, right? Max length minus 1. Yeah, that works. So we'll just show input sequence once. This is going to be now a one hot encoded array. So as you can see, so let's say I have this array, right? This corresponds to one vector, and as you can see, each of these arrays are orthogonal to each other. If you take their like if the angle between them is 90, you can sort of check it by yourself. Um, so now that like we've established that the orthogonality of these arrays is there, you can sort of see that when you want to calculate mean square error between two arrays, I'll actually do one and show you. One sec. So how do I calculate mean square error here? So I'll do input sequence 1 minus input sequence 2 square, and the whole thing is power 0.5 and weird. Oh, we've squared the mid. Never mind. Oh, 1 off 1, right? That's the problem. Alright, we'll see this as we calculate loss. Back to this. Right, we need to put these all to torch. Um, sequence torch dot number sequence, and same with target sequence. By target sequence. Now we can put these to code. Right, dot number. What? Alright, there are already two. I mean. Now once I ran it once, already put it to cooler, but once I ran it again, it was now that it was already on the GPU, and it was trying to say from NumPy, it wasn't in NumPy anymore. It like wasn't a NumPy type array anymore. That's why this error is being thrown. Um, so yeah, essentially both sequences, input and target, are now on cooler. So you can ignore the error. This is just the consequence of running it twice on something that is memory dependent. Okay, so now that we've run the model, we just need to run a standard model training segment, right? Same as previous ones as well. Model.train with label gradients. As a dot zero grad. This is to prevent gradients from accumulating. Go ahead and now standard epoch class. Not view. This one shape minus one. I'll explain this in just a second. Why I'm rearranging all of them to sort of I'm sort of flattening the arrays. I'll explain that in just a second. And as you'll probably see once I print them out, you'll be able to see why I'm happy to do this. Um, this is a question of this does it for you because it does it this. So I'm using like a version of Copilot for Colab. You can check it out if you like. I think there's one which is enclosed. Yeah, this bracket is enclosed. It's forward. Yeah, it doesn't need hidden nodes. I don't see where the loss is constant. This does not seem right. Oh, wait, we can do this. Right? Order of parameters and get faster. Run this entire thing again just to be sure. So what happened here? Why the loss was constant was because this where was the yeah here the model dot parameters were the same as before, which is incorrect because we didn't want to take place there anymore. Now the error is reducing properly. So like just to be sure, we'll sort of make number of epochs 200 and try it again and see whether error is going down. Right, and error is going down further. So our model essentially works. Now how do we test it, right? So we'll just pick a couple inputs from here and just look at what the output shape is looking like. And as you can see, it's 3, which is the number of sentences we had, times number of, I think this was characters in each, and this was the padded length. Or I think the padded length was 15, something along these lines. So the reason why we need to flatten it, right? Because otherwise I'll have to like write a for loop and calculate loss for each thing and append it again. But if I just print output here, this looks terrible. But you can see like this is the length of each, what do you call it? This is the length of each character in the array, and this is the entire sequence itself. And there are going to be 3 such sequences. So I hope that makes sense. And okay, so the reason there are 17 is because there are 17 100 coded values, 17 total characters, right? Um, so we should be good there. And just to get an idea what the target sequence is supposed to look like. Right. So I hope everybody is clear with what we've done so far, right? We've created the model, we've one hot encoded the values. Ignore these errors, these are just pushing to torch, pushing to CUDA. And we sort of looked at why we're doing one hot encoding, right? So I hope everybody's clear so far. After this, it's just a question of getting predictions from our model, and we're essentially done with today. So we'll write a function for this, and I get into a little bit more of RNN like concepts, just so that we clear on everything. So, and same reason why we want hard encoding, because our model only accepts them in like one hard encoded values. So characters, number of unique characters. And shape. Now we'll put it in model.eval. Again, just to recap, model.eval disables gradients, and disable gradients so that when you're testing, it doesn't, there is no loss, right? You're not computing loss for while testing, so it can't really do backprop, but because it is still going to be calculating backprop, the gradients will be affected. So we don't want that to happen. So we shift to model.eval. Now an important thing what we'll be doing here is out. So out comma hidden model factors. So out is your output, right? Total. And what this is going to be is an array of something like this, except it's going to be one hot encoded. How do we figure out like which one we should be taking? Because this is going to be a probability distribution, right? So what we need to do is we need to create a probability distribution across what it feels is actually correct, because the model won't be giving you anything with 100% certainty, right? So you need to create a softmax, which is going to give you a probability distribution now. And from that, we'll take the one with the highest priority. So we'll just take the arguments of the highest probability. Character index and start arguments.
Could you explain why we're using softmax again?
Sure. So I'll actually show you what out.hidden is after that. Then you'll be able to sort of see. So I'll just print it out here so that when we run it, you will see that. And then you'll see why we need a softmax, because your model is going to be predicting something, right? And you will see what, and then you'll be able to see why we need a probability distribution for that. I will copy the rest of the code out here because it's sample code. This is just generating a sample, so not a. And then we'll run a sample. Right, so your model hasn't used any activation function at the end there, right? If you go through the model here. Right, it's not used any activation functions here, which means that what it's predicting so far is just absolute values, what it thinks will be there. Printed here are values, let's say So this is the absolute values, right? So it's predicting 9.249, 2429, or minus 4.9. So not lying between 0 to 1, and therefore not probabilities, right? What your softmax is doing is converting all of these absolute values, or this entire vector filled with absolute values, to a distribution between 0 to 1. So I'll actually print that out also, so that, right, so we'll print out as well, and we will print out this time. You will see that, right. So now, as you can see, these are all lying between 0 and 1 and are representing the actual probability of what is taking place there. Does that make sense?
Yes, it
I think if
does.
you I think if you get rid of this, this might still work. I'll just try that out though once. I'm not entirely sure. It's not being it's right. It's taking a while for some reason. It will fine just now. Mm, one element in this. I'm just gonna run out to see whether there's any issues with something that's been stored in memory. Yep. I'm just gonna start Stack Overflow. Did this. a tensor, so we'll need to convert that. So what is sort of the problem here, as you may have seen, that certain things are on the GPU while others are not, while certain things are tensors while others are supposed to be Python scalars. So that's sort of what I'm just struggling with here for a moment. Okay, so what I'll do instead is I'll show you the one which I haven't, which I wouldn't say done properly, but the one where this issue isn't coming. So I'll just show you the outputs there. The code is exactly the same, and when you test this on your system, if you, I think you do it entirely on CPU, it will definitely work. If in case there's any discrepancies, I'll make sure it's corrected for the lab sheet. So I'll just show you on the lab sheet itself. So this is the lab sheet which works. Right. So as you can see, so this is my input like array, right? I've put in hey, and it's predicting the entire sentence, which is hey, how are you? Now, if I just put in h, for example, so it's predict have a nice day. This is because while training have a nice day is probably been is probably has a stronger gradient than hey, how are you? Even if I run this multiple times, it should give me the same output. It will give me the same output every time because neural networks are deterministic in terms of inferencing, right? In the sense that there is no randomness associated with a certain set of weights once gradient descent is stopped, right? There is no weight changing. Therefore, whatever is your input at any given point in time, there will be the same corresponding output every single time. So let's say I now put um, right? This will give me have a nice day. But what the problem is now, let's say if I put in y, this is going to give me a sense of gibberish. Why is that? Because our model hasn't been trained on a large enough data set for it to recognize sentences that are like larger than just those three sentences. So if I start like making my data set much larger, it will over time eventually be able to generalize to a large number of sentences. So will give me exactly the sentences. Let's go through what are, I've forgotten what are three sentences or not text. Right. If I put G, for example, it should predict good, I am fine. So essentially what we've seen today are a couple things, right? We've seen We looked at the difference between neural networks and RNNs. There's one more thing I need to introduce, which is the different types of RNNs that are possible, right? Um, as you can probably imagine, RNNs can be used for a variety of different things. So starting with like you can have single inputs to multiple inputs, multiple outputs. You can have multiple inputs, single outputs, right? Um, and I'd actually recommend that you spend a minute thinking about this and probably writing down a basic graph for it on your on pen and paper, um, because it will give you a different, it will give you a better idea for how you could possibly use RNN in different scenarios. So I'm just showing something on my screen now. Is this visible?
Yes.
Yeah. So you can sort of have a one-to-one RNN, which is pretty straightforward. You can have a one-to-many, which is what we're doing, right? We're having a single input. Oh, so sorry, we're doing a many-to-many, where we have multiple inputs. So I have H, E, Y, for example, and then it's going to be predicting what the next three or n characters are. You can have multiple types of many-to-many networks. You can have many-to-one also, which is sort of the time series example I had given earlier, right? You can give multiple time series inputs, so t minus 2, t minus 1, t, and you want to predict what the next value is going to be. So this is your t plus 1 output. Your ideal, your model predicted t plus 1 output.